Swayam Prabha. Digital India. Educated India.
So, here we continue with our discussion on virtual memory. If you recall, in our previous lecture, we discussed the basic motivating factors as to why we need virtual memory, and we started our discussion on one of the very popular virtual memory schemes, namely demand paging. Now, we continue with this discussion, and in this discussion, we discuss some more aspects of demand paging that we had started discussing in the last lecture. Now, one thing we discussed, if you recall, there is something called page faults, page fault exception. A process is trying to access a memory location, CPU is generating an address. In the page table, you find that the valid invalid bit is marked as invalid. So, the hardware will be generating an interrupt, an exception. Control will transfer to the operating system. OS will be loading the page and will come back and restart the instruction, execute the instruction that caused the page fault again. Okay. So, let us look into some detail the different steps as to how this page fault interrupt or page fault exceptions can be handled by the operating system. Because as you know, every time an interrupt occurs, control transfers to an interrupt handler or interrupt service routine, which is part of the operating system. Okay. Let us see what is the first step that results in page fault. First step is the CPU is generating some addresses, there is a memory reference. The CPU is trying to access a memory location. From the memory location, you see that is the logical address, there will be a page number and an offset. From the page number, you can access the corresponding page table entry, and what the corresponding page table entry is showing? That corresponding page table entry is showing that the valid bit or valid invalid bit is set to invalid I. Currently, the page is invalid, which means it is not in memory. Then the so called page fault exception is raised. This interrupt is generated. So, as I said, whenever this interrupt is generated, there is a standard procedure for handling interrupts. Control transfers to an interrupt handler or service routine, that is part of the operating system. So, we say that the control transfers to the operating system. Okay. Now, as I said, there are two reasons why this bit can be set to invalid. Either it is a valid page within the process address space which is currently not loaded in memory, or it is altogether an invalid page, like that hole I discussed in the previous lecture between the heap and the stack regions of a process space. There is some space there is some block in the address space where nothing is stored, that is an invalid region. Okay. So, now after that interrupt arises, the operating system has to decide, and for decision operating system will be maintaining another table. It will consult another table, because it will keep track of which parts of the process address space is valid, which is invalid, which part does not contain any data, it will keep track of that. So, it will decide that which of these two is true, whether it is an invalid reference, that means you are trying to access a memory location which is not a valid access within the process address space. If it is so, then there is something wrong in your program, you are trying to access an invalid memory location. So, typically some error message will be generated and the process will be stopped, process will be aborted. But the second one is more common, that the entry was marked as invalid because the corresponding page is currently not in memory. If it is the second case, then you continue with the next step, step 3. Step 3 means you have to load that page in memory. For that, operating system, the first step it needs to do is to find a free frame where to load it. Memory will contain many page frames. It will identify some page frame which is currently empty, currently free. But if there is no free frame, as we mentioned earlier, we will have to remove one of the frames from memory. That one frame we are removing is referred to as the victim page. Okay. So, once we identify the victim page, we will have to exchange that victim page with the requested page. So, we swap the requested page from the secondary memory with this victim page. But when the swapping occurs, that victim page need not be written into the secondary storage all the time. Only if it is updated or modified, then only it will be stored. So, after you load the page which was initially invalid, now it will become valid. So, you will have to update the page table entry by changing that corresponding flag bit from I to V, and after doing everything, you will have to return back to the program which caused the interrupt, and you will have to restart that instruction that caused the page fault. Okay. So, this is how whenever a page fault occurs, the operating system responds. These are the different steps for handling a page fault. Okay. Fine. So, pictorially we are showing the same thing here. Let us say here on the left we are showing a process. Let us say the process is executing an instruction, load some memory location M. Okay. This M corresponds to a memory location. So, whenever the CPU is trying to read from that memory location, again there will be a page number and an offset. With that page number, this is the step 1. It refers to a page table entry. This is the page table. It refers to a page table entry, and it is found that currently the entry is marked as invalid. So, this will be generating the page fault interrupt, which is the trap. This is number 2. When that interrupt is generated, control will be transferred to the operating system. Operating system will identify which page is to be swapped in, which is the page that is to be transferred from secondary memory into physical memory. So, this is step 3, to identify which page has to be brought from secondary memory to primary memory. Before actually bringing in, it will also have to identify a free frame. Suppose here I am assuming that there is a free frame existing, otherwise you will have to also identify a victim page for removal. Here we are ignoring that victim thing, we are assuming that physical memory has some free frame. So, it locates that free frame and brings in the requested page. This is the swap in operation. And once it brings in, it will have to reset the page table. This is step 5. So, what do we mean by resetting the page table? See, once it is loaded into some of the free frames, let us say the free frame number is x, let us say. It will be storing this value x in the corresponding entry in the page table. And secondly, this I flag, this will be marked as V. Now, this will become valid. So, it is like this the page table will get updated. And lastly, it will return back to the program that caused the interrupt, and it will restart the instruction. This load M has to be executed again, that is the restart. Okay. This is how the overall thing works, starting from an instruction generating to a page fault, to handling the page fault, to returning and restarting the instruction. Okay. Fine. Now, there are some issues and aspects for demand paging that need some discussion. So, at the beginning when a process starts, now the question is, how many pages do we allocate to a process in the beginning? We are saying that we are not loading the whole process, that is all right, but do we load a single page? Do we load the first 5 pages? How many? So, when a process starts, what is our strategy? See, the exact strategy can vary from one operating system to another, how the OS is configured. Normally, what happens is that when a process begins execution, the first few pages are loaded, they are allocated space in memory, with the expectation that the first few pages are the one that will be executing first. The instructions in the first few pages will be executing once. But you also do not need to do this. The other alternative is the extreme case. Extreme case means you start with no pages in memory. No pages in memory means that all the page table entries are marked as invalid, 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 invalid. Okay. Now, the operating system tries to execute the program from the beginning. How does it do? It will use some kind of a jump instruction. Basically, the program counter, as you know, the program counter always points to the next instruction to execute it. So, operating system makes the program counter or initializes the program counter with the address of the first instruction. Basically, the PC points to the first instruction. So, when the first instruction tries to execute, it will result in a page fault right away, because none of the pages are loaded. So, that first page will be loaded, the page fault interrupt handled, and it will be returning back, and that first instruction again restarted. So, that way the first page will get loaded, and all other subsequent pages will get loaded on demand. So, either of these two you can follow. Either the operating system will proactively load the first few pages in memory and then start. So, whatever pages will be required later will be loaded later, or it starts with none of the pages allocated. As the instruction starts executing, immediately there will be a page fault, immediately a page will be loaded, and this process will continue. It will be loading other pages whenever they need. Okay. Now, to have this, there are some hardware support that you need. First thing I said, you need the valid invalid bit with the page table. So, one thing you remember, what we say is that in the page table, now we have something like this. I said there are two entries, one is the frame number, and here I am saying the valid invalid bit. We said earlier that page table is typically stored in memory, in physical memory, but if you visualize the page table like this, what I am saying is that only the first part of the page table that will be stored in memory, but the second part, this valid invalid bits, they need to be stored in a high speed register inside the memory management unit. Why? Because whenever a instruction address is generated, automatically you will have to find out whether it results in an exception or not. If the page table is in memory, every time you will have to access the corresponding entry in memory, read from there, then see bit is invalid or valid, and then an exception has to be raised. It will take a long time. So, this all additional bits that are there in the page table, typically they are implemented as hardware registers. Okay. And there can be some other flag bits also, this we shall be discussing later. Like for example, I said some of the pages may be modified while it is in memory. Those are called dirty pages. Some pages which are loaded, they are clean, you write something on it, it becomes dirty. So, if it is dirty, they have to be written back into the disk when they are swapped out. This is one thing. And the second thing is that instruction restart facility has to be supported by the computer organization, by the architecture. So, from the page fault handler, when you are returning back, you have to come back and restart that same instruction. And thirdly, we mentioned either swap space or any other part of the secondary memory where you are storing the entire process address map, the process address space, you have to access the process pages from there. That support also should be there. Okay. Now, there is another very interesting thing. Now, you may say that in the extreme cases one page is sufficient for a process to run. You start with one page, let the first few instructions start executing in the first page, let them finish. Then when the next page instruction comes, there will be a page fault, next page will be loaded and you can remove the first page. But what I am trying to say here is that there is a minimum number of pages that must be allocated to a process when it starts. If you do not allocate this minimum number of pages to a process, then some instruction, not all, some instruction may not be able to execute at all. There can be scenarios where some instruction may not be able to execute at all. And how many such pages must be allocated? This depends on the instruction set. What are the kinds of instructions the computer system is supporting? Because some instruction may be trying to access memory locations multiple times. That can lead to multiple number of pages and failures. See, there was an IBM 360, 370 class of machines, there was a block move kind of instruction there. That instruction needed 6 memory references for execution, and the 6 memory references potentially can lie in 6 different pages. So, you would need minimum 6 pages in memory for such a block move instruction to execute properly. Not in all cases, extreme cases when all these 6 addresses are in 6 different pages, you need minimum 6 allocated pages in memory. So, some examples are shown here. Let us say we have an add instruction, add R1, 5, which means you are adding some constant value 5 to a register R1. Now, when this instruction is executed, first you will have to fetch the instruction, right, from memory into the processor and then execute it. So, this will require one memory reference for fetching the instruction. So, single memory reference. Let us take another example, load R3 memory location 2500. So, here first the instruction will be fetched, then memory location 2500 will be accessed. So, we need 2 memory words referenced. Third is that you have an add instruction, add memory location 3200, you are adding 5. So, you are loading the instruction, loading the data stored in 3200, add 5 to it, write the result back into 3200. So, here you need 3 memory words. So, the number of memory locations that can be accessed in an instruction, that depends on the complexity of the instruction. More complex the instruction set, this minimum number can vary. So, this is something you have to keep in mind. Okay. Now, the other thing is that you need to keep track of the free page frames in memory, because whenever you have to load a new page, one important thing that the OS has to do is to locate where a free page is there in memory, free frame. So, once it locates a frame, the requested page can be loaded there. Okay. So, basically this is needed when the operating system is trying to allocate memory space for the pages. So, whenever a page fault occurs, some page stored in secondary memory has to be loaded in physical memory. So, the operating system must store in some way information about all the free page frames. Let us call it free frame list. So, when a request comes, request in the form of a page fault, let us say there is a page fault, you need to allocate a new page, a page frame. So, any one frame from the free frame list can be allocated. Similarly, when a process has finished execution or due to some reason is being swapped back into secondary storage, so all the frames that the process was occupying will be released, and all these frames will be returning back to the free frame list. Okay. Now, we shall see typically this free frame list is maintained as a linked list, because this is an efficient data structure to keep track of this kind of dynamically growing list. Some list can grow, list can shrink depending on the requests and release. So, linked list is that operating system keeps a pointer to the first free frame, and from the different free frames there are links to the subsequent frames. This is how it occurs. Let us see how. Let us take a small example and work it out. Suppose this is my main memory, this is my physical memory. Let us say there are many pages. Let us give some page numbers 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9, maybe there are more. I am just showing 0 to 9, 10. Now, out of this 10, some of the frames may be occupied, some of them may be free. Let us assume these frames are already occupied. Let us say 0 is already occupied, 3 is occupied, 4 is occupied, 6 is occupied, let us say 8 is also occupied. So, there are 5 frames which are occupied, 5 frames which are free. Now, it depends in the order these pages are allocated and released. Let us say the operating system will maintain a pointer to the other side to the first free frame in the list, first free frame. Let us say according to the operating system record, the first free frame is 5. So, it is pointing to 5. This frame is what? Frame is a collection of words, 2048 bytes, 1024 bytes, 4096 bytes, some power of 2. So, in that byte, the first few bytes can store the frame number of the next free block. For example, this 5 was a free block. In this 5, let us say I store the number 2. So, as if from 5 I have a pointer pointing to 2. In 2, let us say I store the value 1. So, from 2 there is another pointer pointing to 1. 1, let us say I store the number 7. So, from 1 there is a pointer to 7. 7 I store the number 9. So, So, from 7 there is a pointer to 9. So, you see I am building a linked list. So, whenever the operating system needs a free frame, it looks at the first free frame, takes away 5. So, 5 becomes occupied, but the next pointer was 2. So, now the first free frame will become 2 and the 5 will become occupied. Like this it can maintain. Whenever some process frees some frames, it will be added to the end of this linked list or to the beginning of the linked list, whatever. Okay. This is how it maintains the record. Next, it is very important to understand how the performance of a demand paging system gets affected by various things, because ultimately you are trying to access a memory. By incorporating all these complexities of paging, virtual memory, how much slowdown is happening, how much my computer becomes slower as compared to something without paging, without virtual memory. Let us see. So, we have already mentioned this. Whenever a page fault occurs, broadly there are 3 things that need to be done. Of course, there are a number of steps, but broadly there are 3 steps. One is that whenever a page fault occurs, there will be interrupt generated. You will have to jump to an interrupt service routine. In that interrupt service routine, some status registers will be saved in stack, etc., etc. Then something else will be done. So, the first thing is service the page fault interrupt. This does not take too much time, mainly saving the status registers, other things. Next thing, which is more time consuming, is you will have to read the requesting page from main memory, from secondary memory, and before transferring it to main memory, you will have to consult the free frame list, whether any free frames are there or not. If you find there is no free frame, you will have to identify a victim page and you will have to remove that victim page first, and then you have to bring that requested page back into memory. So, this is the most time consuming because it involves disk read write operations. And lastly, after you have brought the requested page, you will have to update the page table entry, as I have said, and restart the instruction that caused the page fault. And as I said, the second step, this step 2, is the most time consuming, because it involves input output with secondary memory, which typically is of the order of milliseconds. In the worst case, when you have to remove a victim page and you find that the victim page is modified, you will have to write it back first and then read the requested page. So, in the worst case, you need one disk write followed by one disk read, 2 disk operations. This has to be kept in mind. Okay? Let us see, let us use some simple notations. Let us use this notation P to denote the page fault rate. So, what is meant by page fault rate? Let us say, I am giving an example. Suppose there are 1000 memory references. Okay. You see that there are 1000 memory references CPU is generating, and out of that you observe that there are let us say 150 page faults occurring total. So, you can say that there is 15% of the memory accesses are resulting in page fault. How are you getting 15%? 150 divided by 1000 into 100. This is 15%. So, page fault rate is basically the same thing, percent divided by 100, that means 0.15. 0.15 is the page fault rate. and clearly page fault rate will lie between 0 and 1. 0 means there is no page fault, 1 means all accesses they result in page fault. Then we denote some times. TMM is the basic access time of main memory. It can be 20 nanoseconds, it can be 50 nanoseconds, 100 nanoseconds, depending on the type of memory, how fast it is. And whenever a page fault occurs, I said you will have to jump to interrupt service routine, do some things and then do the handling of the page swapping. So, the basic page fault overhead we are denoting as a TPFO. TPFO means all this saving the status, etc., all these things, coming back and restarting the instructions. And overhead for swapping out a page and swapping in we refer as T swap out and T swap in. Swap out means this T swap out will occur only when you are trying to write back, when the page is modified. Now, you see how you can estimate the effective access time now. There are two scenarios. You have two scenarios with a probability p, you are having a page fault. With a probability 1 minus p, you are having no page fault. So, you do a weighted sum, you will get the effective access time. If there is no page fault, 1 minus p multiplied by the corresponding time. If there is no page fault, how much time it is taking? It is access time of main memory. Plus, if there is a page fault, then how much time? Your overhead of this page faults, overhead of swapping out, overhead of swapping in the worst case. But here you can make a refinement. Here I am if we assume that there is a page fault, there is a page table and each reference to the page table needs a memory reference. So, actually this TMM will really become 2 TMM, one access for main memory, one access for page table prior to that. Similarly, if a page fault occurs, okay, you can ignore the access time of main memory because the T swap out and T swap in are much larger, whereas TMM is of the order of nanoseconds, TMM can be order of let us say 50 nanoseconds or so. This swap out and swap in times, they can be of the order of few let us say 2 milliseconds. So, maybe 50,000 times larger or so, 25,000 times larger. So, actually it should be plus 2 TMM because after swapping you will also have to access the memory, right. But because T swap out swap in are much greater than TMM, you can ignore this term. Okay. Now, what we shall do? We shall work out a few problems based on this kind of a performance analysis that we tried to show. We shall see that how we can estimate various performance parameters based on different scenarios. So, we work out a few examples, few problems. First one is a very simple problem. So, you see, we consider a computer system with 32-bit logical address with page sizes of 4 kilobytes, right. It is also mentioned that it has 512 megabytes of physical memory. Then there are a few questions. How many entries will be there in the page table and what will be the size of the page table, assuming there is a valid invalid bit with each entry. Okay. Step by step let us see. First let us look at logical address. It is mentioned 32-bit logical address. So, the total size of the logical address will be 32. This is given. But how many bits for the page number, how many bits for the offset? See, it is mentioned the page size is 4 kilobyte, 4 kilobyte pages. How much is 4 kilobyte? 1 k means 2 to the power 10, 4 k means 2 to the power 12. So, for this field will be 12 bits, the page offset will be 12 bits. So, the remaining 20 bits will be my page number, 20 bits, that will make 32 bits. Similarly, if you look at the physical address, it is mentioned physical address is 512 megabytes, number of bits is not mentioned, it is mentioned 512 megabytes. See, 512 is 2 to the power 9, okay. Mega means 2 to the power 20. So, this comes to 2 to the power 29. So, physical address will be in fact less, 29 bits. Out of them, the offset part will be the same because page sizes and frames are the same size, 12 bits. So, remaining 17 bits will be the frame number. Now, let us try to answer the questions. First question is, how many entries are there in the conventional page table? If your page number is 20 bits, 2 to the power 20, this will be the number of page table entries. So many pages are possible. And secondly, what will be the size of the page table? So, if you think of the page table, on this side number of rows will be 2 to the power 20, right, maximum, and it will contain a frame number and a valid invalid bit. Frame number we have already said it will need 17 bits and valid invalid bit will be 1 bit. So, total size will be 18 multiplied by 2 to the power 20, so many bits. This will be the total size of the page table. So, like this you can calculate, right. So, step by step if you go, it will not be difficult, very easy. Let us look at another problem. Consider a paging system where the page table is stored in memory. So, that for every memory access you need 2 accesses. A few things is mentioned. Memory reference takes 100 nanoseconds, that means TMM is 100 nanoseconds. So, you have TMM equal to 100 nanoseconds. How long does a paged memory reference take? See, for a normal paged memory reference where the page table is, where the requested page is there in memory, it will be 100 plus 100, 200 nanoseconds. The first one is for accessing the page table, second one is accessing memory. Okay. Now, it is said that you are adding the translation look asset buffer TLB. So, under TLB what you see is that you have a TLB, 75% are found in TLB, 25% are not found in TLB. So, the probability it is found is 0.75, probability not found is 0.25. This side is found in TLB, not found in TLB. And it is mentioned that TLB access takes 2 nanoseconds. So, if it is found in the TLB, how much time will it take? For TLB access, it will take 2 nanoseconds plus actual memory access after that will be 100. But if it is not found, of course, you will have to access the TLB first, then you find it is not found, then you will have to access the main page table, that is also in memory, that will require again 100, and finally, the actual data in memory another 100. So, this is 102 nanoseconds, this is 202. So, now it has asked to find the effective access time. Effective access time will be, you look at this probability thing, with 0.75 probability access time is 102. So, it will be 0.75 multiplied by 102 plus 0.25 multiplied by 202. So, whatever you calculate, that will be your answer, it will come in nanoseconds. Okay. This is how you can calculate, simple. Let us take another example. Here also we consider a demand paging memory management system where the, well, hypothetically we say, where the page table is held in registers. Registers are inside the CPU. It basically means that this is a small system where the program sizes are small, number of pages are small, so that you can keep all of them in a register bank. But what actually it means here, indirectly it is mentioned that you can ignore page table access time. Why? Because accessing registers is much faster than accessing memory, main memory. Because page tables are stored in registers, accessing a particular page table entry from a register will take hardly a few nanoseconds or even less than that, fraction of a nanosecond. Okay? Now, a few others are mentioned. It says it takes 8 milliseconds to service a page fault if an empty frame is available or the replaced page is not modified. That means, you will not have to write back, swap out, disk write is not required. But it will take 20 milliseconds if the replaced page is modified. So, a few other data is provided, memory access time is 100 nanoseconds, and it is also mentioned that page to be replaced is modified 70% of the time. So, the question is, what is the maximum acceptable page fault rate for an effective access time of no more than 200 nanosecond. See, here let us, the page fault rate we will have to find out. Let us assume P denote the page fault rate. So, let us draw that probability tree first. If P denote the page fault rate, then with the probability 1 minus P, there will be no page fault. And with the probability P, there will be a page fault. Now, when a page fault occurs, now we have another decision whether the page to be replaced is modified or not modified. So, here from here again there are two possibilities. I am writing like this, not modified, not M, or modified M. It is mentioned is modified 70% of the time. So, modified means here it is 0.7, not modified means 0.3. Okay. Now, if it is not modified, it says it will take 8 milliseconds, but if it is modified, it will take 20 milliseconds. Okay. From this diagram you can easily write down the expression from effective access time. Suppose there is no page fault. What is the probability? 1 minus p. So, 1 minus p multiplied by what is the access time of main memory? Main memory is registers. So, for page table access no time, accessing memory it will take 100 nanoseconds. Memory access time is 100 nanoseconds. So, no page fault 100 nanoseconds. So, 1 minus p into 100, I am writing in terms of nanoseconds, 1 minus p into 100 plus, if there is a page fault, p into, now this whole thing. Now, here again there are two cases, modified or not modified. If it is not modified, 0.3 multiplied by, see actually it will be 8 milliseconds plus accessing memory, but I am ignoring this time, this is so less, 100 nanoseconds, this also 20 nanoseconds plus 100 nanoseconds, but I am ignoring this nanoseconds. So, this 8 milliseconds in terms of nanosecond means what? 1 millisecond is 10 to the power 6 nanoseconds. So, 8 means 8 into 10 to the power 6 plus with 0.7 probability it is modified. So, here 20 into 10 to the power 6. This is the total expression for the effective access time. Now, the question is that this access time has to be less than or equal to 200 nanoseconds. In this expression, solve for p. This is what you have to do, right. If you solve for p, you will get the acceptable page fault rate such that the effective access time do not cross 200. Actually, this will be less than equal to 200, you can say, right. This will be inequality. So, you will get some value, p will be less than equal to something. And so, you can try solving this. Okay. And just one last problem here. Here we are assuming page tables are stored in physical memory, main memory, not in registers, and the main memory has an access time of 100 nanosecond. The TLB it says can hold 8 page table entries, and TLB has an access time of 10 nanoseconds, and it is mentioned 85% of the time the page table entry exists in the TLB, and 2% of all the references lead to page faults. Okay. This is what is mentioned. Now, there is a TLB coming into the picture over and above the virtual memory thing. So, let us try to make the probability tree here. Whenever memory access is done, first TLB is consulted, right, not the page table. First you see whether the requested page information is present in TLB or not. It is mentioned 85% of the time it is there in TLB. So, the first step will be with a probability 0.85, it is found 0.15. So, what does this mean? It is found in TLB and 0.15 not in TLB. Now, if it is found in TLB, how much time will it take? Because TLB access time is 10 nanoseconds, you get the frame number, and 100 nanosecond memory access time, you access the word. So, it will be 10 plus 100. This will be the total time if it is found in TLB. Now, if it is not in TLB, then you have to go and access the page table. Now, while accessing the page table, there can be page faults, the requested page may not be in memory. So, here again not in TLB, there are two possibilities, page fault, no page fault. It is said 2% results in page fault. So, on one side 0.98, one side 0.02. 0.98 means no page fault PF, 0.02 means page fault. So, if there is no page fault, then you get the frame number from the page table itself, which is in memory. So, here the time will be 10 for accessing the TLB, 100 for accessing the page table in memory, and finally 100 for accessing the word. But if there is a page fault, it is said average time for page replacement is 2 millisecond. So, for page fault it will be again 10 for TLB, 100 for accessing the page table, which will generate in page fault, then 2 milliseconds to load the page, and finally 100 to access the memory. So, because these are nanosecond and 2 milliseconds, this is approximately 2 milliseconds, because millisecond is much larger than nanoseconds. So, here your effective address access time will be, just follow this diagram, 0.85 multiplied by 110, 10 plus 100 plus 0.15 into, there are two possibilities, 0.98 multiplied by, this is 210 plus 0.02 multiplied by 2 milliseconds, means 2 into 10 to the power 6. Find out what is the value, that will be your effective access time, and this will come in nanoseconds, right. So, this is how you can approach the problems related to demand paging, which can involve TLB, which can involve page faults. It is always better to draw this probability diagram first, this tree structure first. So, you know what are the probabilities with which different things happen, and straight away you can do the weighted sum. Find out for each path in the tree how much time it is taking, and then you can solve it. So, just essentially from the beginning you see that the first step is coming in a typical demand paging implementation, it comes as the TLB access. So, which can result in TLB hit or TLB miss. If there is a TLB hit, you do not have to do anything. From TLB hit you can do main memory access. But if there is a TLB miss, then from here you have to do page table access. Page table access, again there are two things, one is page fault, no page fault. No page fault means the page is there in memory. So, from no page fault you can do now main memory access. But if there is a page fault, then you will have to handle the page fault handling. Page fault handling means you will have to bring the requested page into memory, and only after that you can do main memory access, right. So, these are a few things you can see, you can do it step by step, and once you understand the process, it will be easy for you to draw that probability tree diagram, with which you can solve almost any problem that is given based on paging or demand paging. We come to the end of this lecture, where if you recall we discussed some aspects of demand paging, and towards the end we worked out some problems as to how we can find out the performance of the demand paging environment in terms of the effective access time of main memory and the different overheads. One thing we did not discuss so far, we mentioned the idea about victim page. Whenever there are no free frames in memory, we have to select a victim. Now, selecting the victim is a very important task, because as I said earlier once, that if I select a victim page as 1, I replace it, but immediately afterwards I request I need that page again. So, I will again have to bring it. So, there can be a lot of page swapping in and swapping out, leading to very poor memory access overall utilization. So, we will have to select that victim page in a very careful way. In the next module, we shall be starting our discussion on a number of such victim page selection algorithms and some other aspects of demand paging again. So, we shall be discussing them in our next lecture. Thank you.